The information economy has arrived. The world is teeming with innovation as new business models reinvent every industry. InsideAnalysis is your source of information and insight about how to make the most of this exciting new era. Learn more at InsideAnalysis.com.
InsideAnalysis.com.
And now, here's your host, Eric Kavanaugh.
All right, ladies and gentlemen, welcome to the future indeed. Your host, Eric Kavanaugh here. What a wonderful show we have lined up for you today, and the only coast-to-coast radio show all about the information economy. It's called InsideAnalysis. Got my good buddy Krishnan from 6 Sense Advisors. We're working on some cool stuff these days. And we have Chris Gladwin, the CEO of a company called Ocient that is fundamentally changing the data warehousing landscape. So we're going to dive into what that all means for you, how it's going to help you get your business done in the near future. And really, I wanted to talk about the evolution of data warehousing. So Krish and I are old enough to remember all the different eras we've gone through. It used to be that a data warehouse took you 2 years to stand up, or sometimes a year if you were very good at it, cost you millions of dollars. Don't even bother trying unless you have that kind of expense. And then things started to change. We went through this whole Hadoop world that we've talked about on the show many times, where people thought, oh, NoSQL, is that not only SQL or is that NoSQL? They thought that that MapReduce, which is how Yahoo indexed the web, could be used to do a lot of fun stuff with data. And they did. There were some interesting use cases that came out of that. But then cloud storage dropped precipitously in price, and that kind of killed the value proposition of Hadoop, which was already a bit of a kludgy environment. And then what happened? We had this massive resurgence of SQL. So for those who don't know, SQL stands for the Structured Query Language. It is the lingua franca, if you will, of database query languages. It's how you query a database to understand what's in it. And this whole surge came out with a company called Snowflake, which at the time had, I think, had the biggest IPO in this industry ever. Now that's come back down to earth a bit. And then you've got this company, Databricks, that comes along. Then you've got Amazon Redshift. There are all these different ways that you can slice and dice data and do your data warehousing. So what makes sense for your company? And then this new company, Ocient, comes along, not exactly new. They were on version 19 a while ago. I think they're in version 21 now, which shows you the maturity of the platform. They came up with something called a hyperscale data warehousing. So what does that mean? Well, the cloud gives you this hyperscale capability, right? So people started to understand that Google and Amazon and Microsoft, they're the hyperscalers for being able to deliver functionality at tremendous scale that can scale up. Increasingly, it can scale down. That was a bit more of a challenge than scaling up. But what does that mean for data warehousing? Well, we have the man to explain all of that, dialing in from my old haunt of Lamont, Illinois, Chris Gladwin of Ocient. Tell us about your vision and what is hyperscale data warehousing?
Hey, Eric, great to be here. Krish, great to talk with you. So hyperscale is a term that I think has been used at different times because it changes in its meaning. What we're seeing is what hyperscale means in data analysis is it's the point at which the scale of the data analysis dictates a different approach. You can't just take the normal kind of middle of the road and say, well, let's just make it bigger. There's a point at which the scale of your data analysis benefits from an approach just for hyperscale. So that's one thing we see. And where we're seeing that in the market is generally when the average amount that you're analyzing is about a petabyte of data. So every time you run a query, it's got to look at a petabyte. And you do that a lot, and you're doing kind of complex things. And in terms of numbers, what we're seeing is we have gone through the process of identifying what are all the data sets in the world with business requirements that need that. And we're seeing it's about, on a dollar basis, it's about 4% of the overall $210 billion data analysis market. So it's about an $8 billion market, growing really fast. It's growing not only because the data keeps growing, but the number of use cases that need that approach is growing. So it's growth on growth. So it's growing about 35% a year to about $35 billion in just 5 years. So that's the market. And then you get into like, what's in there? What is the kind of data that needs this? And certainly we're seeing the biggest source of that is telecoms themselves. So if you're a telecom, your network is giant. And there's all kinds of reasons why you want to analyze what's going on. It could be compliance requirements you have. It could be capacity planning, troubleshooting, performance optimization. But to really do that, you got to look at all the metadata that flows in your network to see what's happening. And the amount of metadata that a telecom makes is crazy. It's not trillion scale. It's hundreds of trillions, and quadrillions is the next number. That's actually what they want to analyze. So that's just a little flavor of kind of what hyperscale means.
Yeah, you bring up an excellent point, because there are these inflection points in the industry, right? And so historically, you'll see things like that's where appliances would come into play, right? When the software can no longer handle it by itself, you do an appliance, and then you're leveraging the power of the hardware and the software. And then, of course, that kind of changes again. And so you innovate on the software. And as my business partner, who's mostly retired now, Robin Blorwood, once pointed out, all the innovation starts at the hardware level. At some point, some new piece of hardware changes things. And we were talking before the show about solid state memory.
Yeah.
And if you look at, there's a lot of interesting threads we could pull here, but you look at Hasso Plattner, and this is a bit off topic, but he saw like 20 odd years ago, 25 years ago, he said, you know what, memory, like solid state, is going to come down in price over time. And at a certain point, it's going to cross with data stored on disk. And so they pushed SAP into this whole in-memory world. Well, it's before Kubernetes came out. And so now they're, kind of sitting on this monolith in a new distributed world. It's a bit of a different challenge, but he saw that coming, and you've kind of seen that coming too, right? Because the capacity of these flash, of these solid state drives to deliver data much, much faster with less trouble is a big deal. So, but figuring out how to build the infrastructure to leverage all that, well, that's what you guys have been working on for 20 odd versions, right?
Yeah, we saw that coming almost exactly 10 years ago. The revolution that's happening in solid state wasn't something you could hide, because it literally was close to a $50 billion investment made by semiconductor manufacturers like Intel and Samsung and Toshiba. Like, that doesn't hide in a corner. That's like $10 billion fabs and thousands of engineers and, lots of academic papers. And it took a long time. And so one of the things that's different, though, about this, what I would argue, it's the first new building block in computing ever. You hard drives, and they got bigger, and DRAM got bigger, but solid state, it's not a faster spinning disk. It's not cheaper DRAM. It's different. And, you could see it coming from a decade away. And unlike most of the time, or I think pretty much I'm curious what y'all think, but I would assert that this is the first new semiconductor change that didn't start like in supercomputers and work its way down. It went the opposite. Apple, as a phone manufacturer, device manufacturer, and Samsung also saw this coming, and they got in the production. They were investors in the fabs and the fab companies, and part of that was like, I get first crack at it. Yeah. So what we saw as, a company completely dedicated to building a data analysis platform on solid state. And we have friends. I mean, we've been doing this for a million years. And there was a point where it was in your phone. It was in like billion unit production scale in consumer product, the phone, the laptop. And we, as the leading technology creator for hyperscale data analysis platforms, we could barely get our hands on samples. It just wasn't in production. Like, consumers were first.
Wow.
And then what happened? And then you had the supply chain issues with COVID, where, that just made it really hard to get something unless you had a guaranteed contract.
Right.
And then about 12 months ago, it changed. Now you want 1 million, no problem. Those fabs are running. They've got the production issues. And the profound change that you were referencing is what's happening now is it's gone from really hard to get your hands on to you can get as much as you want. And there's two metrics that matter. One is the cost per storage, and the other is cost per performance. And what is happening right now is, if you look at the lifecycle costs and include not only the cost of the drive, but the cost of power, because they're more efficient on power than spinning disk, the space, which costs money to put in a data center, and they're more efficient on space than spinning disk, and reliability. When something fails less often, it costs less. In solid state, fails less often than spinning disk. If you look at that life cycle cost, solid state particularly NVMe solid state, which is the parallel interface that everyone uses. It's a great standard.
Right.
Is crossing below spinning disk right now.
Wow.
On a cost per terabyte basis, with currently 2,000 times the performance. And the next generation will have 4,000 times the performance, then 8,000 times the performance, and spinning disk will never get faster. So that's happening right now. And what that will cause, and it'll first happen at hyperscale, is the collapse of compute and storage tiers into one. And the only reason they were separate because there was a big price difference. And then what we can talk about maybe later is around 2030, the cost per performance, which, we were using the cost per million random 4K reads per second per dollar, solid state will drop under DRAM, under the cost for performance.
Wow.
And solid state is so early in its Moore's law curve that it is in Moore's law. Every 18 months, it gets twice as good. DRAM is not, spinning disk is not. They're kind of stuck. And so this is where we are today, and where we're headed is solid state is going to completely change, how computing is built and how data is analyzed.
Yeah, that is absolutely fascinating. I'm going to bring in Krishnan to comment on that. I mean, these are the kinds of things that engineers need to be focused on. And frankly, CDOs and CTOs and CIOs need to have in their perspective, because this is going to have tremendous impact on what you're able to do if you're not embracing this new way of doing things. But Krish, what do you think?
Oh, absolutely agreed. In fact, to highlight where Chris was taking the thought process to, if you want to think of in the next 7-year spectrum, 2030, right? What's going to change? The question is what's going to change? That's what bothers a lot of CIOs and CDAOs, not just the digital officers, but the data analyst. What's going to change? We're becoming drone driven. Everything is getting automated. Everything is becoming its own lat longs and its own points where data is going to intercept and crisscross, and what boundary is safe versus what is okay, where's public versus what's private. When you're looking at those boundaries exploding in the next 7 years, we're going to look at volumes of data, which is like, yeah, I built a 5 terabyte data warehouse. People will laugh. 5 terabyte would be like something that happens on a daily basis. I built a 5 petabyte data warehouse. Now you're going to be talking, yeah, that's good. But then we're going to be talking about 50 petabyte data warehouses. But we'll still say data warehouse, right? I mean, so to me, while the spectrum of storage is fantastic, the problem solving still has to be put on top of it so that you can tether and then get the solution stack built on top of that foundation. And to me, that's where, Eric, I think we should take our next set of discussion points with Chris is why data warehousing?
Yeah. Well, that's a good question. So I'll throw it over to you, Chris. Now you have these data lakes people are talking about. There are these large language models doing very interesting things, but it's not data warehousing for sure. And you're really focused intently on the data warehousing use cases at hyperscale to enable organizations to really slice and dice, right? Because the thing is, the faster you can cut through the data, the faster you can do the analysis and get the answers, the more questions you can ask, the more chance you have of finding the signal you wanted to change your business, right? And I think a lot of the older solutions now are frankly encumbered not just by bureaucracy, but by technical debt and sort of traditional hurdles that they're just not getting over. They're kind of running into walls. That changes behavior inside the organization. You ask less questions, you're less risky, if you will, you take fewer chances, and then you don't do as well. I mean, that's my take on it, but what do you see, Chris?
What we're seeing in customers is the compromises they've had to make at hyperscale often involve things like, letting most of the data fall off the table. I mean, they can't effectively analyze it, so they don't even collect it. Automobile manufacturers, if you have 100 million cars, I talked about telcos. For a telco prior to Ocient in this next generation of data warehouse capability that we're talking about, they really couldn't cost effectively collect and analyze all network metadata on the network. It's a quadrillion rows in a table. It just doesn't make sense. They're not going to spend $500 million on a supercomputer. And so therefore, then they end up making compromises. So if you want to do like performance analysis, you don't care about averages. All you care about is the worst. What's the worst performance on my network and what were the conditions? But that means you actually have to have all of it to see the worst and identify the things that correlate with the worst. So what we've seen where, companies would then either just not have all the data and then make the best of it. In some cases, like in ad tech, some of our customers, they would there's tens of millions of digital ads that go up for auction every second. And there's whole industries of people that either supply those inventory of ad placements or buy those and analyze those. And because, that's such a volume, if they want to back test an algorithm for some kind of campaign they're going to run on the last 3 months, well, that's just too much data. So then they would downsample it to something like 0.1% of that ad exchange. But the problem with that is, then if you had a really large customer that wanted to, test a campaign, the results become inaccurate. So what we're seeing is because at Ocient, we're using this solid state technology, which is like game changing. It's, and going back to your comment earlier, the best you can do as a software designer is to go as fast as the hardware. And so what we're able to do is to address these problems where you can do full resolution data. Results can be accurate, even at hyperscale.
Yeah, that's fascinating stuff. I mean, really, and I'm sure there are some mindset issues that companies have to kind of get over, but the person in the room who understands the challenges, the person who has run into these barriers, and to your point, has had to say, well, let's just use 0.1% of the data. I mean, downsampling always gets you that lossy characteristic, right? Where it's like, well, am I now going to lose visibility into the signal I was trying to find in the first place? Well, that's not a very effective solution. And again, to be able to do it quickly, and what you mentioned, a stat like 2,000 times faster, some of these new solid state drives are compared to their counterparts. Well, that's more than an order of magnitude. That's
three orders of magnitude.
Orders of magnitude, right? It's like it's off the charts kind of, and it fundamentally changes the conversations that you have and how your team operates. And so that's what excites me, is you're opening this new portal for companies that go down the hyperscale highway with data warehousing to where you don't have to limit yourself to small views of the world. And that is going to fundamentally change how and it saves tremendous amounts of money. If they can gather all the metadata at telco and do real or near real-time analysis, you could wind up saving millions, hundreds of millions of dollars just in not wasting money, not wasting time, not wasting energy. Folks, we'll be right back. Don't touch that dial. You're listening to Inside Analysis.
Welcome back to Inside Analysis. Here's your host, Eric Kavanaugh.
Take us to the future. All right, folks, welcome back to Inside Analysis. Your host here, Eric Kavanaugh, talking with Krishnan and Chris Gladwin of Ocient. Krish is my consultant friend from many, many years ago, also in the Chicagoland area. I grew up in the Chicagoland area. And, before the show, we were talking about I-355 and how I-355 opened up, and I used to be the editor for the Lamont Metropolitan newspaper. And I actually interviewed a guy from the Illinois Department of Transportation about the project at the time. And he told me something very interesting. He said that the laws do not allow you to go and build a highway according to future traffic speculation, like how much traffic you think is going to be in the future. They said you can only use the data of traffic that is currently in this region. And that's how you justify where you build these highways. Well, once they built 355, I promise you, there were all kind of people that changed their driving habits because it was so much easier to go up to the north suburbs. And it was like night and day, basically. And you can kind of make this comparison, this loose comparison of traditional versus hyperscale. Like traditional is going the back roads and hitting stoplights wherever you go. It takes you an hour and 10 minutes to get from Bolingbrook to Schaumburg. And then the hyperscale shows up. It's like, oh, nope, you just get on the highway. There's no turnoffs. You can just keep rocking and rolling and get there in no time. It changes behavior and new things happen. And you start to change how you plan your day, because I don't have to spend an hour and 10 minutes. I can only spend 27 minutes. So these new technologies, Chris, when they come along, they open up whole new possibilities. So it's not just that you can do the old stuff 10 times faster. It's that, yeah, you can do that, and you could do all this other interesting stuff. And that's where the business value tends to accrue. What do you think?
Yeah, generally what we're seeing is by designing a new software data analysis engine for hyperscale analysis using this amazing new building block, the NVMe solid state drive, as well as some other pretty choice building blocks like high core count CPUs and 100 gig NIC connections everywhere, you really can't get to 10 times the price performance than what was previously available. And in some cases, you get to 100 times. And every time, this is not the only time there's been 10 times the price performance for some kind of IT capability. It's happened many, many times. And every time it happens, two interesting things occur. One is industry or consumers never keep doing what they were doing before and just save the money.
Right.
Never. They always find, if it's 10 times the price performance, they will find more than 10 times the things to do with it. And the pie grows bigger. I challenge you to, give me a counterexample because I'll name everything else. So that always happens. And the other thing that's interesting and part of why that happens is when you look back 10 years, 20 years later, at what are the uses now of that disruptive new technology, typically at least 80% are new, things that could only exist once the disruptive technology change occurred.
Right.
20% or less are what was there before becomes bigger, faster, cheaper. And more than 80% becomes only now that I have broadband, can I have a giant system that distributes videos of pets known as YouTube and other silly things like that couldn't happen before broadband. Broadband happens, boom, here comes YouTube. And there's, many, many examples of things like that. Like we, in my last company, CleverSafe, we dominated the market for photo sharing, for software for photo sharing systems. Photo sharing was kind of the first incarnation of cloud storage. It could, there was this idea of like, take as many pictures as you want, we'll store them forever. And every once in a while, we'll sell you a mug. Like that business cannot exist. And that's a very great business for a lot of companies. It couldn't exist until the price performance of, super reliable photo storage systems at hyperscale went down about 100 times. And you just, you just see example after example where when these big disruptions occur, all kinds of new innovation happens.
Yeah. No, that's exactly right. And I love the comment you made of, when you do get this increase in performance, never do they just save the money, especially in analytics, Krish, because in analytics, again, you're trying to understand your business. And so now when you have these new tools to dig deeper into your own data to understand, like you take the telco example, that's a big deal. If you can problem solve faster and figure out how to fix this issue, you're not going to lose 1,000 or 2,000 customers to your competition, for example. And just little things like that really add up quickly. But it's the case across the analytical spectrum. The more you can analyze, the better off you're going to be. And the fact is that some of these old solutions, even though Teradata, for example, I'm told just spent $250 million to refactor their entire engine to run in the cloud and Amazon Web Services. Now they just rolled out for Microsoft recently. That's a lot of money to spend refactoring. But Chris has some interesting thoughts about Kubernetes as well, because with Kubernetes, you're federating all this compute, which, I've always joked we sacrifice state at the altar of scale to be able to do these things. But still, there are inefficiencies baked into that system as well. So if you do your job right on the Ocient side, there's really not a lot of benefit to get from going into a Kubernetes environment. All you're trying to do is enable your analysts to crunch data. Chris, I'll throw it over to you first, and then we'll get Chris.
Yeah, and the point you're bringing about the availability of valid data is very essential, right? I mean, for many years, we've all gone in the traditional route where we've said, yeah, this model works, or no, this one doesn't, or while a bridge table suddenly becomes a point where data just goes crisscross, all kinds of issues that have been faced for a number of years where analytics could not succeed because of the lack of data in the bottom line.
Right.
That is something that I would love to hear Chris talk about, because hyperscaling would mean now your data fabrication, right? This is a term that Ocient would love to talk about with a good definition. So Eric, if we can get Chris to give us a quick definition on what the data fabrication thought process is, and then we talk more about why, then bringing the analytics use case or anything else is going to be so much more easier for folks to understand. But that's the bottom line. That's the grassroots that we want to get to. Chris, over to you.
Yeah, Chris, go ahead.
I think the other big change we're seeing in data analysis, kind of from a traditional, even the kind of recent generation of data warehouses like Snowflake and Databricks and Redshift, is a shift from kind of traditional batch-oriented data loading to data never stops streaming at scale. And the database now has to exist in this environment where data is constantly growing. And that, one of the challenges is taking, terabits per second of input data, which is never in an easy to digest state, and getting that transformed from some typical semi-structured, messy state into, relational schema that is indexed, secondary index, compressed, encrypted, and showing up in queries within seconds. That traditionally has not been possible either. And that's another thing that we were able to do at Ocient, because it's also interesting to think about, where does data come from? And at hyperscale, 0% of the data comes from typing. People don't type at hyperscale. Just to give you a sense, a minimum system for Ocient would be, a petabyte, 1 trillion rows in a table. 1 trillion, if you print it out, circles the earth 73 times. And if you were to scroll it, 2 pages a second, assuming you could see data that fast, it's centuries to just scroll through that table. Like, that is not something that humans can create, and that is not something that humans can even read. So a couple changes there, in that all the data being analyzed at hyperscale is machine generated. It's routers, it's cars, it's satellites, it's instruments. And then the other big change is we've entered this time. It used to be like, if you really had to look into something, you could go look at the logs. You could actually go look at the data. Like, you can't go look at the data anymore. Human beings cannot see data at this scale. They are now completely dependent on these tools that look at the data for them. And an increasing amount of what people are using is machine learning, artificial intelligence, to characterize that for them. I can't look at everything. So just go look at these 100 trillion things and tell me what's 4 standard deviations out of normal. And maybe I can look at that, but I can't look at the raw data ever again. So those are a couple giant changes we're seeing.
That's funny. You have a couple great quotes now. I can't look at the raw data ever again. That's a funny thing. And let's talk about observability too, because you were just kind of referencing that. Observability is this huge space now that has blown up for lots of different reasons. But to your point, with observability, you've got all these signals of data that's streaming constantly. And what you're trying to figure out is how to apply the appropriate filters to get signals when necessary. So you mentioned like 4 levels of deviation, for example. Can you talk about how you're able to leverage data warehousing technology at hyperscale in order to enable meaningful observability across these systems? And there's also the issue of cloud environments, which have lots of different things going on. It's not just your ERP you have to worry about, or one database. It's lots of different things interacting in real time to push this stuff forward. So talk about how you're able to help people understand what's happening in that world and how that actually works.
Yeah, an increasing amount of what's happening is what's happening right now. You can't just be, data was, fresh from yesterday. It's got to be fresh from 3 seconds ago. And so, so much of what you want to understand involves this fresh data. So it's sometimes just looking at that data itself, and sometimes it's looking at that data in comparison to older data, but it's less and less just looking at older data. So this, real-time analytics capability that we've incorporated at hyperscale into our platform is essential. And all of our customers are using it now because all of them have, this need. And the big unlock we're seeing in there, just like we're seeing in the data analysis at hyperscale, is using machine learning more and more to tell you not only what is in the data that's pouring in all the time, but how to deal with it. It takes, there's so much coming in, it's changing so much that we're using AI more and more to help us load and characterize the data as it streams in.
Classification, basically, right? So you're trying to classify in real time and ascertain what's normal and what's not normal. I mean, I think that's basically the rule of thumb, right? This is normal behavior. Now, if something gets out of whack, that's abnormal behavior. What's going on there? And this is how you have to figure out how to use these different filters to classify and to understand in real time. And so let's think about Larry Ellison, for example, who I guess 5 years ago was talking about the self-healing database, right? That was their big thing. It sounds like you're kind of going down a similar path where you're using machine learning and AI to ascertain, wait, something is wrong over here. Let's go fix that, reset this, no, do this, do that, whatever. Is that kind of what you're talking about? Is this self-healing capability?
Yeah, and I would say that that self-healing thought from 5 years ago, kind of the universe there is that this database is a sometimes fixed data set, and that's what we have to heal.
Right.
What I'm reporting is that the world has changed to where so much of the part of the database isn't just what's there, but what's arriving. So that the healing that you have to do the static part's actually pretty easy. It's a lot harder to deal with like what's going on now and as that changes, because the world, like, it doesn't matter what the data set is. If it's, vehicle data, there's road construction, there's traffic, there's a public safety incident. If it's, ad tech data, something's happened in the market. So like, how's that change, the buying and selling of ad placement? If it's
interesting,
it just like, you can't remove the dynamic nature when you think about anything, even, including just like, what does it mean to heal? What's the kind of harm that you got to fix? Well, it's more in the flow of data as opposed to the batch of data.
That's very interesting. And that's true, right? I mean, data is always moving. It always has been moving, but you made a good point, because the old mindset was, okay, here's this static database that I have, and something broke. Let me fix this static thing. Like, no, this thing is moving constantly. It's always moving. So you're trying to really understand the flows of data. What is the nature of this flow of data in this particular environment, and point that over to, like you say, some event. Well, what happened? Let's get to the bottom of this. That's really a magical characteristic of these modern systems. What do you think, Krish? Go ahead.
No, the other piece to what Chris was saying, I think it was about 18, 20 months ago, I was working with the San Diego Department of Biological Sciences. They said they were trying to capture shellfish brain movement into the database. They had an issue. They said, we don't know how to make this effective. And I spent like almost a week trying to understand what were they trying to get. To Chris's point, right? I mean, if you don't know what you're trying to get, everything is going to be like, oh, it's outside this. Once we ascertain what we were trying to get in that constant flow, we could then say where the spikes were, where the abnormalities were, where there was an interception that needed to be done. All kinds of pieces could be reacted to, but you need to have somebody who knows the system really well in order to understand what is it that you're missing, so that you can take care of it at that very minute. I mean, it's a latch on ASAP. There is no, it can wait for something to come. No, it's like, do it then, do it there. Absolutely.
I'm now really understanding why Chris uses this term hyperscale. And in a past show, we had people define hyperscale, and one guy said loss of control. And that's kind of what you're talking. It's not loss, but you just have to think of things differently. But don't touch it down, folks. We'll be right back. You're listening to Inside Analysis.
Welcome back to Inside Analysis. Here's your host, Eric Kavanaugh.
All right, folks, back here on Inside Analysis, a fascinating conversation with Chris Gladwin of Ocient and Krishnan of Sixth Sense Advisors. We're talking all about hyperscale. Hyperscale is data warehousing. There's an ocean of data now. It's not a problem if you have the right approach. And we had a great question from one of our studio audience members who mused, if we're never going to be able to see the raw data again, the question of analyzing behavioral anomalies or lineage and trustworthiness comes up pretty quickly, like intrusion detection or regulatory compliance, et cetera. And in the break, you made a really good point, Chris, about how the whether it's compliant or not is never going to be in just some field in a database. It's always an assessment based on multiple pieces of information. And to your point, at the scale of information flow these days, it's going to be a complex layering of decisions based upon the data, right? Go ahead with that explanation.
Yeah. So if for example, you want to do intrusion detection, it's not like there's a data field somewhere in a database that says intrusion detection, yes or no. I mean, you have to look at like a whole bunch of raw data, and there might be a couple layers of analysis. There's the analysis, then there's the analyzing the analysis that says that is an intrusion, and it characterizes that. So that's really what you're trying to get at, is this meta information. Is it an intrusion detection? Is this a risk? Is this trustworthy? Those are higher level things, like you're building a credit score, for trustworthiness or business risk analysis. Well, that credit score might have 1,000 different variables that go into it, and each of those variables might have, 1,000,000 data points or 1,000 data points that go into it. So that's really more and more what you're seeing is, the raw data is not the thing that has business value. It's the analyzed result.
Yeah, no, that's exactly right. And you also made a really good point about just this new building block and the NVMe solid state drives and the interface, and how it's literally the opposite of spinning disk. Can you explain that to our audience? Because it's a very compelling story. Go ahead.
I mean, something we've asserted at Ocient for the last 10 years, since we've been hearing about a real solid state drive, the parallel interface, the NVMe is the name of that, non-volatile memory express, which is now, like I said, it's in your phone, it's in your laptop. It went from nowhere just a few years ago to it's in everyone's phone now. Wow. And that's also different, because normally that kind of new technology, where it's new physics, new materials, starts in supercomputers and works its way down to consumer products. And here it just started in your phone, which is pretty amazing. And one of the things we think is profound about it is we at Ocient, we assert that it's really the first new building block in computing. And as we were talking about earlier, hardware at the end of the day is what dictates price performance and what happens. And all you can do as a software architect and developer is make your software go as fast as the hardware can go. You can go no faster than that. And the way that NVMe solid state works is basically, as you were just saying, Eric, exactly the opposite on how a spinning disk works. A spinning disk is like a record player, and it has a read-write head that sits in exactly one spot, exactly one time, and it sucks or spits bits onto that, onto or from that media. But it is in one place at one time. So physically, what it wants to see is a serial stream of things to do, a serial sequence, one after another, because it's only in one place. Databases, when you're doing a count or a sort, or the things that databases do on the inside, shuffle, they actually want you to do a whole bunch of random parallel operations. But what the whole multiple generations of databases, data warehouses had to do was to figure out how to take what you want to be multiple parallel things and have them happen one thing at a time on a spinning disk, because anything in volume was on a spinning disk. Solid state is exactly the opposite. It doesn't want one thing to do at a time. The prior versions wanted 256 parallel tasks. Now they want 512, headed to 1,024, and so on. Parallel tasks per drive, thousands and thousands of times a second. It is exactly the opposite. So what that means in terms of your database, your software, is what I'm describing is the interface between a primitive database operation, like a shuffle or sort, and the physical drive. That's called your IO layer. Mm-hmm. Okay. And if your IO layer has to treat your storage media exactly the opposite, what it means is you got to rewrite your whole IO layer. And that's 40% of a database. So if you really, you could take an old architecture and set it on spinning disk. Mm-hmm. Or take it off spinning disk, set it on solid state. It'll run 10 times faster, but it should run 10,000 times faster. You're just leaving orders of magnitude. Now you got to write your IO layer. What you'll find if you rewrite your IO layer, which we did at Ocient, Next thing you know, you're going to have to rewrite your memory allocators in Linux because they're not designed to flow this much data.
Right.
Next thing you know, you're mucking down around with the actual assembler driver for that IO, that NVMe solid state drive. And you also have the thing called vTune, which is the thing that you use to tune the Intel CPU just right with the, the caching layers. Like you're down there. Like there's no further down than where you are in the computing stack. And then you have to go up from there. So the next thing up from the IO layer is, we call it the virtual machine. It's the thing that once your parser kind of parses out your query, the parser will give you, the parsed query down to this virtual machine, this optimizer, and it's going to have to figure out how to drop it down to the IO layer. So that's the thing that figures out every query can be done in an infinite number of ways. So to think about all the different ways and maybe think about it for half a second and then decide, all right, this is how we're doing it. And then down you go to the IO layer. So, that's another 40% of your database. So, like parsers are not exactly rocket science right now. You can go find a nice open source parser, but you end up having to rewrite your whole database stack, down to the memory allocators if you really want this thing to go. And that's what we had to do at Ocient. It took us, because it always takes at least 5 years. It took us 5 years. That's why you were saying version 19 was our first production version, because it really was 19 versions.
That's amazing.
But that's what you have to do.
That's amazing. And, I'm reminded of a couple things. One, I had Dr. Michael Stonebreaker on this show, and it was a long time. It was probably like 10, 12 years ago. And at that point in time, he said 80% of the code that is written should just be thrown away. And what he was talking about is what you're talking about, that as the hardware layers change and as we get new building blocks to play around with, those old software applications were designed to work in much different environments. And so how you design this thing to do calls and to pull and do all polling or whatever it is that you're doing, that has to be cognizant of the new stack, if you will. And to your point with these NVMe, because it is completely different, because it wants lots of things in parallel, you have to rewrite stuff. Yeah. And it takes a lot of time to go all the way down to that level. But unless you do that, you're missing huge chunks of potential optimization along the way, right, Chris?
Yeah. And, I used the word assembler recently in that answer. How often does that happen?
Yeah.
In 2023? And, that's just a little bit of code down there, at the Linux layer. But the database itself, we had to rewrite in C++. And it's not like we don't know that takes longer. It does take longer. But let me tell you, if you have like 2 seconds of garbage collection and you're running a query where, I don't know, you're going to look at 50 trillion things and you want an answer in 10 seconds, that means you're looking at 5 trillion things a second. You garbage collect for 2 seconds and you got 10 trillion things to go put somewhere.
Wow.
Like that's not going to work. So, next thing you're down there in C++ and you're doing all this kind of crazy stuff where you're making everything stateless. So you can just like parallelize to forever. In our system, it is, if you've got 500 tasks per drive. I mean, these are little solid state drives. You can put 20 of them in a U. You can put 20 U's in a cluster. Next thing you get 1 million parallel tasks at every single layer of the stack, and things are flying. I mean, you're doing 5 trillion things a second. So it's flowing up and down that stack. 5 trillion things a second. Million parallel tasks. So each task does a lot of things each second. So it's just nuts. And so building something like that it just takes forever. There's just no way around it.
Yeah, well, because you built to hyperscale, that's another interesting topic in and of itself, right? If you're building for a particular end state, you're saying, I want this thing to run good on this track. But no, you're saying, I want this car to be able to go faster and faster on whatever track happens to come around, right? Isn't that the kind of difference in mindset?
Yeah, we have a customer right now who we've done it on paper, but this is the first time we're doing it. They want a demo with 100 trillion row table. So we're building one of those right now. Yeah, I mean, you design it. I mean, we actually, one of the original customers that we're still working with, because it takes a long time to build something like this. They wanted something where literally it was about a quadrillion rows in a table. And they wanted to run queries that would hit most of that and give answers in like 10 seconds. And yeah, I mean, you're going to do 100 trillion things a second to answer that. So we've designed it on paper, but designing on paper and actually having it run, in the physical universe are two different things. So we're we're kind of hitting in terms of actual scale, like that 100 trillion scale right now. And we've got a number of customers that are like at exabyte scale, which will, get into the quadrillions.
Yeah, well, folks, podcast bonus segment is up next. Look these guys up online. Ocient, Chris Gladwin. You're listening to Inside Analysis.